Hello and welcome to Global Climate Change. My name is Rhonda Plotkin and this is my dog Argos. I'm going to hope that he does not bark at anyone throughout this lecture because he does like to bark when people come to the door or around, so hopefully he won't do that to us. Welcome to Global Climate Change. Uh, we're going to learn some really exciting things this semester. We're going to be learning about the greenhouse effect. We're going to be learning about natural warming as well as anthropogenic warming. We're going to be learning about feedbacks and climate modeling. We'll be learning about mitigation strategies and also the policies that we might enact in order to mitigate climate change. So let's get started here. First of all, each lecture will have, the reading that's responsible for that week or that lecture down here in the bottom left-hand side, as you can see here. And the first thing to go over actually would be the syllabus. So here's our syllabus. See, Meteorology 112. This is going to be the best way to get a hold of me is going to be my email. I do check it quite a few times throughout the day. I do have office hours, as you can see here. If you can't make it during that time, though, please just get a hold of me, email me, call me, whatever, and I will do my best to accommodate you. I do have an office phone number right here. I will be checking that probably periodically throughout the day as well. Textbook, you may have noticed that there wasn't actually a textbook that I put on Canvas for, this course. That's because I tried my hardest to find a free textbook for us. This one is free. We'll be working out of it. That way we can skip the bookstore. I'll let you guys read this description on your own. First of all, since we are using a free book, there will be things inside the lecture videos that won't be in the book. And I need you guys to make sure that you're watching the videos and also taking notes off of these videos because you can use those notes for test times and things like that. There'll be resources. They'll all be put actually on Canvas. Just keep checking Canvas throughout the week, and you'll be seeing things as they pop up. I probably will be putting things up, as often as possible to keep engaged. There's going to be a variety of different ways that I can use to assess you. We're going to use homework. There will be 2 midterms. It's quite a bit of a material, so I don't want to pack it all into one test. So we're going to actually have 2 midterms. There will be a project. This is a project that someone within my department actually came up with. It's a great project. More on that later. We actually will have a whole lecture designated to that. And then there'll also be online discussions and a final exam. You guys should be kind of familiar with this grading criteria. I do teach a few classes here at SJSU, so and I use the same one for every class, so hopefully you're familiar with that. Now the homework, there will be about 10 homework activities throughout the semester. There'll be about 10 points each. The main thing is get them in on time. I have it structured so that you keep up with this class. If you get behind, it is really difficult to catch back up. So if you are late with your homework, it will be reduced 10% and then 25% each day. And that's really for you, to keep you up to date with this class so you're not falling behind. Again, more on this Green Ninja project, a little bit later on. And then here's our discussion. The discussion will also be 10 points each. The thing is I would like you to have your discussion entry for, the week, but I also would like you to respond to one of your classmates. Now, there's about 40 of you in this class here. So, I want you to respond. You'll have actually a lot of chances to respond to different people and different ideas. There should be a diverse group here, so we should have lots of different ideas, which should be awesome and really make this class fun. And then we also have classroom environment. So I put this in here because the topic of climate change could actually be sometimes a little bit controversial. I'm actually from Omaha, Nebraska, so it's more conservative there, and it's definitely more controversial where I'm from. So I just really want to drive home to you guys to please be very respectful to each other. Remember that we all come from different backgrounds and we all have different ideas, and may have taken different classes in science. So please just be respectful to each other and understand that, we're not always right and somebody else isn't always wrong, Okay, now I do want to say that I know it's easy to copy and paste things from the internet, especially when you have an online book, and enter it in as the answer to a question. I will be looking for that. Okay, I want you guys to have your own unique writings and your own unique ideas. That's very important. So please, come up with your own writing, restate it in your own words, things like that. Don't plagiarize, and don't cheat. Now here's our course schedule. As I said, this is, week 0.5, the lecture right here that we're doing. And then we'll just kind of keep going down. You can see that the 2 midterms are here. We do have this week off for Thanksgiving. And then our final will actually be uploaded during this week at the end here. All right. So to get on to climate. All right, so now climate has been mentioned a lot in the news. I actually just did a quick Google search and I found a whole bunch of different things here. Fox guest host, these climate change alarmists have been wrong. Fox's Pete Hegseth says addressing climate change is the left's religion. Scientists bid farewell to the first Icelandic glacier lost to climate change. If more melt, it can be disastrous. Food will be scarce, expensive, and less nutritious, climate report says. So there's definitely going to be both sides of the coin. We're definitely going to have the alarmists, and we're also going to have the deniers. And by the way, this is what they call each other. This is not like what I came up with. But they're going to be 2 different sides of the coin. So we're going to try and sift through this and decide, I don't like to get very political personally. I just like to give the facts, and you guys can decide on your own really what you feel and, what you think about this. But it is an exciting time to take this class because there really is so much different information out there on the internet. I feel it's my job to educate you so that when you do read these things, you can find the loopholes. You can find where it's just really too far to one side or the other. Okay, so this first lecture, we're going to get through a couple definitions here and just some things that you just kind of got to know before we dive into the material. So the first thing is going to be the difference between weather and climate. This is going to be something that I'm going to drive home to you guys. It's very important to understand, okay? Because weather is going to be something that's happening right here and right now, okay? The temperature in San Jose is 70 degrees today. That is weather. Okay, climate is going to be a completely different idea as far as the time period. Climate is going to be more of an average. It's going to be more of a long-term, a seasonal, so something that you would use a statistical term to describe. It also includes extremes as well, though. So my favorite atmospheric scientist, Dr. Marshall Shepard, he coined this phrase, weather is your mood and climate is your personality. And I think that really captures the idea of these 2 terms and what they really do mean. So please keep that in mind, okay? I hear people all the time saying things like, it was really cold this winter, so obviously climate change isn't happening. So that person, though, is not understanding the fact that they're using a weather phenomenon to describe the climate. And those 2 things don't go together. So you can never really describe anything by a certain event or a certain season or one specific year. Things happen. There are anomalies. There's definitely, weather is definitely one of those things that is all over the place at times. Somebody like me being from the Midwest, I definitely know that. It'll be 90 degrees one day and freezing and snowing the next. So, there's definitely extremes to weather. But climate is more of this averaged out. It doesn't have all these little wiggles inside the line. It'd be more of, a linear, a nice straight line. So watch out for people when they say that. So like we said, the weather is going to be the state of the atmosphere at a particular place and time. We use different variables actually to describe weather. We're going to use a variable like temperature or relative humidity, wind direction, or wind speed. We might even say cloud cover. Obviously the cloud cover is going to be different, or it is actually different today than it was yesterday. I live in Mountain View, and yesterday it was super sunny and beautiful out, and today it's cloudy. So those do change day to day. But climate is going to be the long-term average, okay, including extremes. So we're going to use more variables like the record high temperature, or the average relative humidity, the average cloud cover in July, or the record yearly rainfall. So let's look at a couple of examples here and decide what we think actually this is. So it'll be 84 degrees in San Jose tomorrow. Is this weather or is this climate? It's actually going to be weather because we're talking about tomorrow. A specific place and time is here and now. The average rainfall in days in July in San Jose is 0.8 days. So that means how many days on average would actually see rainfall in July in San Jose. This is an average. That's statistical, right? So that's going to be actually referring to the climate. How about the lowest temperature in San Jose on record is 19 degrees Fahrenheit, set on December 22nd, 1990. Put that one in there actually because I was interested to see what the lowest record temperature was. So that actually is going to be climate because it's looking at an extreme. Okay, this is going to be the record. So it's definitely going to be looking at climate. All right, so some more definitions here. I told you you're going to go through a few definitions. First, that the word theory does not mean the same thing scientifically as it does in regular, speech that you might have with your friend. Okay, so let's kind of revisit the scientific method for a moment. I think it's always useful to do that because we don't always think about that if we're not scientists. The scientific method is going to start with an observation. Okay, and then based off of that observation, you might ask a question and form a hypothesis. And then once that hypothesis has actually, been written down, then you're going to try to form a prediction off of it and run some experiments. But those experiments are either, these results from the experiment is either going to be good or bad. So if they're bad, then we're going to reject the hypothesis. And then we're going to go back and form a different hypothesis. But if they're good, then we're going to go to a theory. Okay, so a theory actually is something that's been tested. It's been tested quite a few times in the past, and it's known as the truth in the scientific community. Let's look at a few examples actually of what theories there are out there. Evolution is a theory. Gravity is a theory. So is the Big Bang. Big Bang Theory. There's a whole show about it, right? Okay, but gravity kind of, it might throw you off a little bit, right? Because you're like, oh, wait, isn't that a law? But that's because the Newton's law of universal gravitation can be used to calculate how strong the pull is. When you're doing these calculations, you're using that law for sure. But it doesn't tell you why or how. Why or how is something falling when you drop it? That's where the theory comes in, okay? The theory of general relativity is the thing that it does explain why that thing is falling. So gravity actually is still a theory. Okay, here's two other definitions for you. Climate change and global warming. And many people say to me, I don't understand. Why did they change the name? This and that. Actually, that's what you guys' homework is for this week, is to read a nice little article about that. But, climate change is actually going to include the natural warming that happens as well as anthropogenic. So let's go over the word anthropogenic. That means human-induced. What are we doing to increase the temperature? Okay, or decrease, I guess. We could either way. Human-induced is what anthropogenic means. So climate change will be natural plus human-induced ways that our climate will be changing. Where the global warming actually means just what we're doing to affect the climate. Okay, just anthropogenic only. That's it. It doesn't look at the natural ways that our climate might warm. Okay, so the other thing that we need to go over is units. Meteorology, climatology, the atmospheric sciences, we actually use both metric and English units, but mainly metric. So you need to know how to convert between the two, how to go from metric to English and how to go from English to metric. Most of these big equations that we use in the atmospheric sciences, you need to take the readings or the data that comes in from Fahrenheit, convert it to Celsius or Kelvin, do your calculations with it. And then if you're going to report it back to, someone who might not know meteorology or might not understand the science as well, we might need to convert it back to Fahrenheit because most people in the United States, we think by Fahrenheit, we don't think by Celsius. So temperature, you do need to know Celsius and Fahrenheit. Kelvin is used, but we won't use it in this class. The distance, we're going to go between kilometers and miles. Kilometers is going to be the standard metric unit, and that's, what we use pretty much all the time in the sciences. So you need to know how to convert between those two as well. Now, these are actually going to be the conversions, okay? Like 1.6 kilometer equals 1 mile, 1 kilometer equals 0.62 miles. And then if you want to convert between Fahrenheit and Celsius, you just take the Celsius here, okay, pop it in this equation, and it'll, give you the units in Fahrenheit. Here it also will do the opposite. You pop in the Fahrenheit, and it'll give it to you in Celsius. So let's actually do a little bit of practice. Yesterday's high temperature in San Jose was 65 degrees. What is the value of that temperature in Celsius? So I want you to pause the video. Actually, I have one more for you here. California is about 800 miles long from Oregon to Mexico. How many kilometers is that? So please pause this video, go back to the last slide, do your calculations, and we'll see if you're right. Okay, so the answer to number 1 is 18.3 degrees Celsius. And the answer to number 2 is going to be 1280 kilometers. But how did I derive that? Or how did I get to that? Here, I tried to put down basically, the calculation, how I got to it, step by step, so you guys can see, how I did it, depending on what number you guys came up with. But, it's important to keep in mind, it's a different calculation to convert changes in temperature. In climatology, we do use, the change in temperature or, the change in pressure, mainly the change in temperature though, to describe, what's happening to our atmosphere and to describe, what the temperature is doing. So when you do convert a change in temperature, this delta right here, is a symbol basically for the change. So, to convert the change in, by 2 degrees Celsius or the change in temperature by 3.6 degrees Fahrenheit, you only need to do the multiplication or division. You don't actually need to add or subtract that 32. Makes it a little easier for you, I guess. Okay, so a note on these temperature scales, I kept mentioning Kelvin, Celsius, Fahrenheit. You might be familiar with one or the other. Kelvin was the first one, described here, but, Celsius is going to be, and Fahrenheit, the other two mainly ones that we use. A little interesting fact for you here, negative 40 degrees Celsius is going to be the same as negative 40 degrees Fahrenheit. But, the Celsius scale was actually built around the freezing point of water. So the freezing point of water is actually going to be 0 degrees Celsius or 32 degrees Fahrenheit. Okay, this right here is the freezing point of water. Okay, but if you look at the boiling point, that's up here. It's going to be 100 degrees Celsius and 212 degrees Fahrenheit. Okay, you can kind of see there's a couple other different, record high temperature, which actually was in Death Valley, California. Let's see, a hot day, the average body temperature, average room temperature, right about 68 degrees. Lowest temperature recorded right here is negative 129 degrees Fahrenheit. That's just really cold, right? So these are basically our 3 scales. I'd focus more on looking at the Celsius and Fahrenheit, though, and how they relate to each other. But when we're talking about temperature, what am I really talking about? Like, what do I really mean? Like, okay, so if it's 68 degrees Fahrenheit, what does that really mean? Temperature is actually going to be the measure of the average kinetic energy of a substance. So how fast are these atoms or molecules moving? So in colder air, you can see over here, it's going to be more condensed, okay? And those atoms will be moving slower. But in warm air, it's going to be way more expanded. It's going to be a bigger bubble of air. And these atoms within it are actually going to move a lot faster. I actually have a nifty little animation right here, which will show us that. So if I start, down here at a low temperature, it's supposed to be like an oven, okay? 279 degrees Kelvin. We can look at the mean molecular speed in miles per hour, okay? This is going to be 1,277. You can see how these molecules are just kind of moving around, okay? But watch what happens when I get it warmer. If I can grab the little thingy, I always have a problem with that. finally. So we're going to warm it up in there to 415 degrees Kelvin. I'm sure you saw as I was fussing with it and got it to work. You know, these atoms started moving a lot faster. Okay, there definitely is a definite visual difference between them. You can see that the speed actually sped up, or the speed of them moving around sped up to 1,558 miles per hour here. So kind of nifty little visual when I can get the knob to work of how these atoms actually react to the temperature change. All right, so I think that is everything for this lecture. I look forward to, like I said, having you guys in class this fall. Signing off right now, and have a good weekend. Bye.